Hi everyone, here we're going to discuss the friction lab. So let's see the different components here. So um, let's say that this is a rough surface and you have an object on the ground. So on an atomic scale, if you zoom in here, even if it's a smooth piece of metal, if you zoom in on an atomic scale, it's not perfectly smooth. There's like little teeth on an atomic scale here. And the interlocking of the teeth between this block and the floor, that is the source of friction. So let's look at the forces that are going to be present here. First of all, this object has a mass m, so it's going to have a weight. And next, this object is in contact with the floor here, so there's going to be a normal force, Fn. So depending on, sometimes you might see normal force written as Fn, or you might see it written as N. I'm just going to call it Fn. And other than that, if you're trying to pull the object in this direction, the friction is going to act backwards in this direction here. And so friction is going to depend on two things. It's going to depend on how rough the floor is. So friction is going to depend on two things: how rough the floor is, and the roughness is, we're going to define that by the variable mu, which is called the coefficient of friction. So friction is going to depend on two things. It's going to depend on how rough the floor is, or the coefficient of friction. And the other thing that's going to depend on is how much contact there is with the floor. You know, if the box is this big here, it's going to have less contact with the floor. And the amount of contact with the floor is represented by the normal force. So friction is going to depend on how rough the floor is, but also the amount of contact with the floor, or the normal force. So we're going to begin with we're going to continue with the case when, not when the block is stationary, but when the block is sliding. So here, let's say that you have this rough floor, and you have the block, and you're applying a force F here, and friction is acting backwards. So here, this is going to be sliding or grinding. Or the technical case for this one is we're going to call this the kinetic case. Here then, friction when they're sliding or grinding, we're going to call this a kinetic friction. And that's going to equal the roughness of the floor, which is in this case is going to be the coefficient of kinetic friction multiplied by the normal force. So this one is going to be inequality. Here, what we can do is, well, actually, I'll wait for that. Let's look at the other case. So the next case is when the block is stationary. So when the block is stationary, so this is the rough floor, you have the block here, and here the block is stationary at first. So imagine that this is a refrigerator. At first, you're going to exert a force on a block, but it's not going to go anywhere. But eventually you're going to keep on having to exert more force until then it's going to start to move. But for a while, you're exerting force, and you have to exert a lot of force in order to get it to budge. And as soon as you get it to budge, then you can let it move easily. So in this case here, when it's static, friction is going to be defined by this equation. The static friction is going to depend on how rough the floor is, the coefficient of static friction, and also again it's going to depend on the amount of contact with the floor, which is going to be the normal force, but it's going to be defined as less than or equal to. The reason why is that you have to exert, when it's stationary, you have to exert a lot of force until you get to a maximum force, and then it's going to start to budge. So these are the two equations that the lab is going to be based on. There's going to be one more, but for now, these are going to be for the first part of the lab. So what's going to happen is that in the lab, there's going to be a rough surface, there's going to be a block, and you're going to apply a force to get the block to move. And at first, and you're gonna the website is gonna give you a display that's gonna plot force versus time. So this is gonna be time, this is gonna be force. So at first the block is gonna be stationary, and you're gonna try to apply a force to get it to move. And what you're gonna find is that you're gonna need to apply a lot of force at first to get the block to move. So as time goes by, the force is gonna increase until you get to a maximum amount of friction. So you're going to get to a maximum static friction, and then after that, then you're going to be able to nudge the box, and then it's going to start to move, and then after that it's going to start to grind. And what you find is that as it grinds across the floor, that's going to correspond to this the kinetic friction case. So then the force is going to stay constant as the block grinds. So that's what so let me make a table now. So you're going to have a series of masses, and for each mass you're going to record the maximum static friction and also the corresponding kinetic friction for a series of masses. And let's see why we need the mass. So this block, there's friction acting on it, there's also the normal force, but also let's see here, the normal force acts upwards, and also because of this mass has because of its mass, this object has a weight, Fg. But this block is only moving horizontally, it's not moving up and down, so that means that the normal force is going to be equal to the weight. So you're also going to calculate the normal force by, so the normal force is going to be the same as the weight. So you're also going to calculate the normal force. And now you're going to create a table. So the basic equation for each case is the friction is going to equal the roughness of the floor multiplied by the normal force. And what you're going to do is use this equation to actually get a value for the roughness of the floor. And the way that you're going to do that is you're going to make a table. Let's see why. So here in this case, if you look at this formula, this corresponds to y, this corresponds to the slope m, and this corresponds to x. So what you'll do is you're going to make a table of the friction on the vertical axis and the normal force or the weight on the horizontal axis for each mass, and you're going to get a corresponding straight line, and the slope of that straight line is going to correspond to the coefficient of friction. And you'll have to do that for the static case and for the kinetic case, but that's basically it. So for each series of mass, you're going to calculate the friction, and you're also you're going to measure the friction forces, and you're going to calculate the normal force. And once you do that, then you're going to plot normal force versus you're going to plot friction versus the normal force, and that will give you a value for the coefficient of friction. And you'll have to do that in one case for static, and on that same table you're going to also plot friction, static friction versus the normal force. So in this case here, this will give you let me make this a better incline. So you're also on the same graph going to get another one for the kinetic coefficient of friction. But in each case, so let me clarify this here. So you're going to plot static friction versus the normal force, and that's going to give you this line. And then you're also going to plot this is going to be kinetic friction versus the normal force again, and that's going to give you this line. And in each case, the slope of the line is going to correspond to the roughness of the floor. So you're going to do this for two different materials, but essentially that's the this corresponds to part A and part B of today's lab.